Good morning. Today we are going to learn touching circles, one theorem about touching circles, and we'll solve examples of practice set 3.2. We'll start with touching circle first and then we'll move towards this theorem of touching circles. We'll start with touching circles first. There are two types of touching circles: externally touching circles and internally touching circles. Now these two circles are with centers A and B. Centers A and B touches each other externally at point C. And there are again two circles with same centers A and B, but these two circles touches each other internally, means the smaller circle is inside the bigger circle, and these are external touching circles. And here same, these two are internally touching circles at point C. These are externally touching circles and these are internally touching circles at point C. Now what is actual definition of touching circles? If two circles in the same plane, these two circles are in the same plane, suppose this blackboard is a plane. If two circles in the same plane intersect with a line in the plane. Now to understand the definition, we have to draw one line which is common tangent for these two circles. Suppose line L is common tangent for both circles. Line L, here also line L is common tangent for both these circles. See once again, if two circles in the same plane, two circles in the same plane intersect with a line, these two circles intersect with a line. The most important part is in only one point, means these two circles intersect with a line in only one point, and that only one point is here point C. Here also these two circles intersect with a line in only one point, means there is only one point common between these two circles and that line, and that is nothing but point C. There is only one common point between these two circles and line. There is only one common point between these two circles and line, that is point C. Then they are said to be touching circles. Now these two are touching circles, but their names are different. For these two circles, these are externally touching circles, and these two circles are internally touching circles. And the line is the common tangent. This line L is common tangent for both circles, means line L is tangent to this circle, line L is tangent to this circle also. The point common to their circles and the line is called their common point of contact. Now the point which is common to these circles and line is called point of contact or common point of contact. Here also point C is common point of contact for both circles and line. This is about touching circles, externally touching circles, and point C is their common point of contact. It is only one point common to these three, that is this circle and line. Here also these two are internally touching circles, and point C is common point of contact for these two circles and this line. This is about touching circles. Now we'll move towards theorem of touching circles. Statement is already written here. Diagram is also same for this theorem. If two circles touch each other, if two circles either externally or internally touch each other, their point of contact lies on the line joining their centers. Their point of contact, that is point C here also point C, lies on the line joining their centers. Means point C lies on the line joining their centers, means here point A and B are the centers, means we have to prove point C lies on line AB, means A, C and B are on the same line. Here also point C lies on the same line, means we have to prove point A, point B and point C lies on the same line. This is how to prove. We'll move towards theorem. If you want screenshot of this definition, then take it. And we'll move towards theorem. Same diagram is used for theorem. Since both are touching circles will take both cases, externally touching circles and internally touching circles also. Means this is about a diagram of this theorem. If two circles touch each other either externally or internally, and line L is their common tangent. Now what is given here? Given point C is point of contact of circles with centers A and B. Here also point C is point of contact of circles with centers A and B. Point C is point of contact of circles with centers A and B. This is given. Now what is to prove here? That is most important. What is to prove? Then their point of contact lies on the line joining their centers. Means we have to prove point C, which is point of contact, lies on line AB. Point C in both cases. Point C lies on line AB. Here also we have to prove point C lies on line AB. For that I'll join AB. It is obviously point C lies on line AB. You can see here point C lies on line AB, point C lies on line AB. But we have to prove this. Now proof is very short. Now line L is tangent to the circle with center A. Line L is tangent to the circle with center A at point C. Therefore AC is the radius. AC is radius, and we know tangent theorem, that is the angle between tangent and radius is 90 degree, that is right angle. Means AC is perpendicular to line L, or line L is perpendicular to radius AC. Line L is perpendicular to radius AC. Similarly, line L is perpendicular to radius BC. Means for this circle with center B, line L is tangent and BC is radius. Therefore, by tangent theorem, line L is perpendicular to radius BC. Line L is perpendicular to radius BC. And for both statements, reason will be tangent theorem. Tangent theorem. Now for this diagram also, line L is tangent to the circle with center A. See once again, line L is tangent to the circle with center A. Therefore line L is perpendicular to radius AC. Line L, this is radius AC. Line L is perpendicular to radius AC. Similarly, for smaller circle with center B, line L is tangent to the circle. Therefore, line L is perpendicular to radius BC. See once again, line L is perpendicular to radius AC. Line L is perpendicular to radius BC. Both are having reason, that is tangent theorem. Now only interchanging these sides, line L is perpendicular to radius AC means radius or segment AC is perpendicular to line L. Only changing sides. And segment BC is perpendicular to line L. Same statement, only changing sides. Radius AC means segment AC is perpendicular to line L and segment BC is perpendicular to line L. Now AC is perpendicular to line L and BC is also perpendicular to line L, but if there is a line, suppose line L and point C here, then how many perpendiculars can be drawn passing through or at point C to this line L. To this line L passing through C, how many perpendiculars can be drawn? It's like this. Suppose this is perpendicular. Like this, how many perpendiculars can be drawn to the line L and passing through C? Is there only one or more than one? Is it perpendicular? Or is it perpendicular? Or is it perpendicular? No. There is only one perpendicular to the line L and passing through the same point. If you take another point, then another perpendicular can be drawn. If you take another point on that line, then another perpendicular can be drawn. But if there is only one point, then only one perpendicular can be drawn passing through that same point to that line. And that is nothing but this one, and these two are not perpendicular. Means only one perpendicular can be drawn passing through the same point to that line. We'll use this property here. Now same diagram here. This is line L and here is point C. Now through C we got here two perpendicular, that is AC is perpendicular to line L, BC is perpendicular to line L. But we know theorem that is only one perpendicular can be drawn through any point on that line. Therefore AC and BC are not on different lines and these are on the same line. Since only one perpendicular can be drawn, therefore AC and BC are not on different lines, these are on same line. Here also, here is line L and here is point C. And AC is perpendicular to line L, BC is perpendicular to line L, and we know only one perpendicular can be drawn from point or on a line through the same point. Therefore, AC and BC are not different lines, AC and BC are same lines. What does it mean? It means point C lies on line AB. Point C lies on line AB. But only one perpendicular can be drawn to a line passing through a point, passing through a single point. Hence AC and BC lies on the same line. What does it mean? Hence point C lies on line AB. Hence point C lies on line AB. Point C lies on line AB means AC and BC are not different, these are on the same line. Since only one perpendicular can be drawn passing through one single point to that line, therefore AC and BC are not different, AC and BC are not different, these are on the same line. Hence point C lies on line AB. Now what does it mean? It means that A, C and B are on the same line, means A, C and B are collinear, or A, B, C are collinear. Hence points A, B and C are collinear. Collinear means lies on the same line. Point A, B and C lies on the same line. A, B and C lies on the same line. But the relation between their sum of the distances is different, that we'll see later. See once again. There are two circles which touches each other either externally or internally. These are in external touching circles and point C is their common point or point of contact. Here also point C is point of contact of these internal touching circles. Point C is point of contact of circles which enters A and B, and we have to prove point C lies on line AB. Point C lies on line AB. Now we know tangent theorem, tangent is perpendicular to radius. Hence line L is perpendicular to radius AC, line L is perpendicular to radius BC. Here also line L is perpendicular to radius AC, line L is perpendicular to radius BC. That is this statement. Reason is tangent theorem. Only changing sides. Radius AC means segment AC is perpendicular to line L, segment BC is perpendicular to line L. Means we will get these two statements. But AC and BC are not different, since through a point only one perpendicular can be drawn to that line. Hence AC and BC are not different lines, these are the same lines. It means that point C lies on line AB. Point C lies on line AB. It means A, C and B, or A, B and C are collinear points. Means A, B, C are collinear points. Now we'll move towards actual meaning of this theorem, or actual use of this theorem. That we'll see. Actual use of this statement. Now for this case, that is if two circles are externally touching circles, if two circles, or if circles are externally touching, then the distance between their centers, now point A is center of this circle, point B is center of this another circle. Now the distance between their centers means distance AB. What is this distance? Is it the sum of their radii? Suppose radius of this circle is 2 centimeter. AC is 2, and radius of second circle is 3. Suppose, then what is distance AB? Is it sum of their radii, that is 2 plus 3? Means if two circles are externally touching circles, or if circles are externally touching, then distance between their centers is equal to 2 plus 3. 2 plus 3 means sum of their AC plus BC. AC means radius of first circle, BC is radius of second circle. Means it is the sum of their radii. Centers is equal to sum of their radii. Means if two circles are externally touching circles, then the distance between their centers is equal to sum of their radii. What about this case? If two circles, or if circles are internally touching, then distance between their centers is equal to now suppose AC is radius of first circle, BC is radius of second circle. Now distance between their centers means AB. How will you find AB now? Suppose radius of bigger circle is 5, radius of smaller circle is 3. Then how will you find AB? How will you find distance between A and B, that is distance between their centers? Is it nothing but 5 minus 3, or AC minus BC, that is radius of bigger circle minus radius of smaller circle. Therefore we get AB is equal to 5 minus 3, that is AB will be equal to 2. Means what is the formula then? Distance between their centers is equal to bigger radius minus smaller radius. It means difference between is equal to difference between their radii. Difference means bigger minus smaller. See once again, if two circles are externally touching circles, then the distance between their centers, that is AB, is equal to AC plus BC. Addition, simple addition. If two circles are externally touching circles, distance between their centers is equal to addition of radii. Now if two circles are internally touching circles, then the distance between their centers is equal to difference. that is bigger radius minus smaller radius, that is AC minus BC. AB is equal to AC minus BC, and here AB is equal to AC plus BC. This is about theorem of touching circles and its use. Now we'll move towards practice set 3.2. Take screenshot. Practice set 3.2, example number 1. Two circles having radii (3.2 centimeter and 4.8 centimeter) touch each other internally find the distance between their centers. Find the distance between their centers. Solution. Very simple, it is for 1 mark. In exam it comes for 1 mark. There are two circles which are touching circles, and these two touch each other internally, means bigger circle and there is smaller circle inside that bigger circle, like this. Then the distance between their centers, suppose center of this circle is here and center of this circle is here. Distance between their centers is equal to difference of their radii. According to this property, distance between their centers is equal to difference between their radii. Difference means bigger radius minus smaller radius. Very simple. Let R1 is equal to 3.2 centimeter and R2 is equal to 4.8 centimeter. Now directly we will write distance between their centers is equal to, since these two are internally touching circles, we will find out difference between their radii. Now which is the bigger radius, that is R2, and smaller one is R1, that is R2 minus R1, that is equal to 4.8 minus 3.2. 4.8 minus 3.2, that is equal to 6, that is 1.6. Therefore, difference between their radii is 1.6 centimeter. Very simple solution. It is for 1 mark in exam. Two radii are given, 3.2 and 4.2, and this is important. These two circles are internally touching circles, and since these two are internally touching circles, therefore distance between their centers is difference between their radii. Difference means always bigger first and then smaller. Bigger minus smaller. And bigger one is 4.8, smaller one is 3.2. You can do subtraction like this: 4.8 minus 3.2 minus point below each other, 8 minus 2, 6, 4 minus 3, 1. That is 1.6 centimeter. No need to take screenshot, you can solve your own. We will move towards second example. It's similar to like this: two circles having radii touch each other externally two circles having radii 5.5 and 4.2, 5.5 centimeter and 4.2 centimeter touch each other externally. Find the distance between their centers. This word is important. Now here these are externally touching circles. R1 is different, R2 is different. R1 is 5.5 centimeter, R2 is 4.2 centimeter. Now since these two are externally touching circles, distance between their centers is the addition of their radii, that is sum of radii, that is R1 plus R2 or R2 plus R1, both are same. Simple addition. R1 is 5.5 plus R2 is 4.2. 5 plus 2 7, 5 plus 4 9, it is 9.7 centimeter. These two words are important. In previous example it was internally touching circles, therefore distance between their centers was the difference, that is bigger radius minus smaller radius. Now here these two circles are externally touching circles, therefore the distance between their centers is simply addition, that is R1 plus R2, that is 5.5 plus 4.2, that is 9.7 centimeter. Now question number 3 is, if you have textbook then read that if radii of two circles are 4 centimeter and 2.8 centimeter, draw figures of these circles. Draw both cases, that is externally touching circles and internally touching circles. Only you have to draw circles of these two radii. In first case you have to draw externally touching circles, like I have drawn in previous theorem, external touching circles and then internal touching circles by taking particular radii. First radius is given as 4 centimeter and second one is given as 2.8 centimeter. Solve this example 3 also. Now we'll move towards example number 4. Example 4. Again there are two circles which are externally touching circles are given with centers P and Q. There are two external touching circles with centers P and Q. Center of first circle is P, center of second circle is Q, and point R is the point of contact. Point R is the point of contact. A line passing through R meets the circle at A and B respectively. Line passing through R. There is a line which passes through R, meets first circle at point A and second circle at point B. Then joining AP and QB. It's about diagram. Prove that number 1, segment AP is parallel to segment BQ, and number 2, triangle APR is similar to triangle RQB. Number 3, find angle RQB. If angle PAR is given as 35 degree. Observe this diagram. There are two circles with centers P and Q touches each other externally at point R. This point R is the common point of contact of these two circles, and there is one line passing through R again, which meets or which intersects first circle at point A and which intersects second circle at point B. Means this is line AB, means A dash R dash B, P dash R dash Q. This is given, and we have to prove AP is parallel to QB or BQ, and these two triangles are similar. In second case, we have to prove these two triangles are similar, and one angle is given, that is RQB is given. Sorry, we have to find RQB, and one angle is given, that is PAR is given as 35. We will move one by one. First, we have to prove AP is parallel to BQ. For that, observe this triangle. This one. Now, what is the type of this triangle APR? What is type of triangle APR? So, what is the particular type of this triangle? Can you find? For that, find out relation between PA and PR. What is the relation between PA and PR? And these two are radii of same circle. Means PA is radius of the smaller circle, PR is also radius of the smaller circle. What does it mean? PA is congruent to PR. PA is congruent to PR means this triangle PAR is an isosceles triangle. Hence, angles opposite to congruent sides are congruent. Therefore, angle PAR is congruent to angle PRA. Since it is an isosceles triangle, these two angles are congruent. Angles opposite to congruent sides are congruent. Hence, angle PAR is congruent to angle PRA. I'll explain first, then I'll write this solution. Means we'll get these two angles congruent. Now, what is the relation between these two angles? Are these two congruent also? That is angle PRA and angle QRB. Are these two congruent? Yes. These two are vertically opposite angles. Hence, these two angles are also congruent. Now, observe this triangle. Now, same like this triangle is also an isosceles triangle. Since QR is radius of this bigger circle, QB is radius of bigger circle. Hence, QR is congruent to QB. Hence, the angles opposite to congruent sides are also congruent. Therefore, these two angles are congruent. Means, this angle is congruent to this one, this angle is congruent to this one, this angle is congruent to this one. Means, all these four angles are congruent with each other, but I want this pair only. Hence, angle PAR is congruent to angle QBR. Angle PAR is congruent to angle QBR. Now, observe these same angles like this. These two are lines and this is a transversal. Now, observe these two angles. This one is PAR, here is A, here is P, here is Q, and here is B, and here is R. What is type of these two angles? And we got these two angles congruent. And what is the type of these two angles according to these two lines and this as a transversal? These two angles are alternate angles, and we got here alternate angles congruent. Therefore, what is relation between these two lines? Since alternate angles are congruent, therefore by alternate angles test that you have learned during previous year, by alternate angle test, AP will be parallel to QP. Since alternate angles are congruent, AP is parallel to QB by alternate angles test. Now I'll write this. Means we got AP parallel to BQ. This first one we have proved. Now we'll write this step by step. Simply we have to take pairs of angles. First pair that we have to take this one, second pair that we have to take this one, third pair that we have to take this one. Statement number 1, statement number 2, and statement number 3. Hence, from statement number 1, 2, and 3, we will get statement number 4, that is this one, this pair. Hence, by alternate angle test, segment AP is parallel to segment BQ. We will write step by step solution of number 1. Angle PAR is congruent to angle PRA. Angle PAR is congruent to angle PRA. Statement number 1. And I am writing this statement directly, then I will move towards this one. Since I am going to write same reason for this one and this one. Therefore, I am writing this one first. Angle QRB is congruent to angle QBR. Statement number 2, and reason for both statements is these two angles are congruent and these two angles are congruent. Reason is isosceles triangle theorem. I have taken this as first statement, this as second statement, and this as third statement. Now we will write this one. Angle ARP is congruent to angle QRB. Angle ARP or PRA is congruent to angle QRB. Statement number 3, reason vertically opposite angles. Vertically opposite angles. Hence from 1, 2 and 3. From 1, 2 and 3, what can I write? These two are congruent, these two are congruent, these two are congruent. Hence these two angles are congruent. That is angle PAR. Angle PAR is congruent to angle QBR. Reason is here, that is from 1, 2 and 3, angle PAR is congruent to angle QBR. Hence, by alternate angles test, since these two angles are congruent, these two are alternate angles for these two lines, and this as a transversal, and since alternate angles are congruent, therefore these two are parallel with each other. Therefore segment AP is parallel to segment BQ. Segment AP is parallel to segment BQ. See once again, simply 3 pairs we have to choose, first, second and third. Hence from statement number 1, statement number 2 and statement number 3, these two angles are congruent. Hence by alternate angle test, AP is parallel to BQ. Very simple. Now we'll move towards second part. That is, we have to prove these two triangles similar. And to prove triangles similar, first step is to write names in triangle APR and triangle RQB. In triangle APR and triangle RQB, what are congruent parts? You can take this pair and this pair. Angle ARP is congruent to angle QRB or BRQ. Reason, vertically opposite angles. These two angles are congruent, vertically opposite angles, and this pair we just proved here. Suppose statement number 4, angle PAR is congruent to angle QBR. Reason from statement number 4. Hence triangle APR is similar to triangle RQB. Triangle APR is similar to triangle RQB by AA test. Simple. Triangle APR is similar to triangle RQB by AA test. Now third one, find angle RQB if angle PAR is given. Find angle RQB, this angle you have to find. If angle PAR is given as 35 degree. Now observe, this angle is given as 35, therefore this one will be 35. This one will be 35 and this one is also 35. Now very simple. Now in this triangle, sum of measures of all the three angles is 180 degree. Therefore angle QRB plus QBR plus RQB is 180. Therefore 35 plus RQB is 180. Therefore 70 plus RQB is 180. Therefore RQB is equal to 180 minus 70, that is equal to 110 degree. Very simple. I am not going to write this here. I will just explain, you have to write it. For third question, one angle is given, that is angle PAR is given. This angle is given, hence this angle is 35. Since these two are congruent, that we have proved here. Or you can move towards directly here also, or step by step move. This angle is 35, therefore this angle will be 35 since these two are congruent. Hence this angle will be 35 since these two are congruent. Hence this angle will be 35 since these two are congruent. Now we want this angle. Hence now in triangle RQB, sum of all the three angles, sum of measures of all the three angles is 180 degree. Therefore 35 plus RQB is equal to 180. Therefore 35 plus 35, that is 70, plus RQB is 180. Therefore RQB is equal to 180 minus 70, that is 100, and RQB is equal to 110 degree. This is solution of third one. It is not written here, you have to write it. Listen once again, this angle is given as 35, therefore this one will be 35, this one will be 35, and this one will be 35. Take sum of measures of all the three angles of this triangle, then you will get answer. Now move towards, or take screenshot of this and move towards question number 5. Which answer of third one you have to solve, you have to write your own. Question number 5. Again there are two touching circles, external touching circles. There are circles with centers A and B which touches each other at point E. Here is point E. And there is one common tangent to these circles, that is line CD, which touches the smaller circle or first circle at point C and second circle at point D. CD. Line CD is common tangent to both circles which touches first circle at point C and touches second circle at point D. And these two circles touches each other at point E. Now what is given? Find the length of CD. Find the length of CD if the radius of the circles are, if the radius or radii of the circles are 4 centimeter and 6 centimeter. Radii of the circles are 4 centimeter and 6 centimeter. I'll join this AB. Now since E is the point of contact, therefore E lies on line AB according to our first theorem of touching circles, A dash E dash B. Now radius of first circle is given as 4, second circle is given as 6. Therefore we'll get AB as 4 plus 6, that is distance between their centers is equal to sum of their radii, that is 4 plus 6, therefore AB is equal to 10. Now we want CD. For that I'll join AC and BD. Now what is angle ACD? Angle ACD. Now CD is tangent to the circle at point C and AC is radius. Therefore by tangent theorem, AC is perpendicular to CD. Now similarly CD is tangent to the second circle with center B and BD is radius. Therefore BD is perpendicular to tangent CD. Means these two angles are right angles. Now we'll do construction here. We'll draw one perpendicular from point A on radius BD or on segment BD. This is our construction. Suppose AE. This is our construction. Solution: draw segment AE perpendicular to radius DB or segment DB. Now the solution is very simple. Observe, we want CD, but what is type of this quadrilateral? What is type of this quadrilateral? CAED. What is type of this quadrilateral? CAED. Now in this quadrilateral, one angle is 90 degree, second one is 90 degree, and third angle we have drawn as 90 degree. Therefore, what is remaining angle? That will be obviously 90 degree, since sum of all the four angles is 360 degree. 90 plus 90 plus 90, that is 270. 360 minus 270. Therefore, fourth angle will be obviously right angle. Now since all the four angles are right angles, therefore what is the type of this quadrilateral CAED? What is type of quadrilateral CAED? It is a rectangle. And opposite sides of rectangle are congruent, therefore CD is congruent to A. Now to find CD, we have to find A first. To find CD, we have to find AE, since CD is congruent to AE, and if you get AE, then CD will be same as AE. Means your target is to find AE first, and that will be same for CD. Now to find AE, observe this triangle. Is it right angle triangle? Triangle AEB. In triangle AEB, AB is 10 centimeter, that is 4 plus 6. AB means hypotenuse is 10 centimeter. What about EB? What is EB? This side. That we'll find. Now since this is a rectangle, CA is congruent to DE. CA is congruent to DE. But what is CA? CA is nothing but radius of smaller circle, that is 4. Now CA is 4, DE will be 4. And what is DB? That is radius of bigger circle. It is given as 6. DB is given as 6. Therefore, what will be EB? EB is equal to DB minus DE. That is 6 minus 4. Therefore, EB will be 2. Now, observe this shaded triangle, which is right angle triangle, in which hypotenuse is 10. One side is 2. Hence, by Pythagoras theorem, you can find out third side, that is AE, and that value is same for CD. Therefore, we will get CD by using AE, and if you and we will get AE by using this triangle, that is Pythagoras theorem. We'll start with this quadrilateral first, and then we'll move towards this right angle triangle. Now construction is draw AE perpendicular to radius DB. Now in quadrilateral CAED, angle or measure of angle CAD is equal to measure of angle EDC is equal to 90 degree. Reason tangent theorem. These two are 90 degree. Reason tangent theorem. This angle is obviously 90 degree. Reason construction. Hence angle CAE is 90 degree. Hence measure of angle CAE is 90 degree. That is remaining angle of quadrilateral. Hence quadrilateral CAED is a rectangle. Quadrilateral CAED is a rectangle. Hence CA congruent to D. Hence CA is congruent to DE. But CA is equal to 4 centimeter. Hence DE is equal to also 4 centimeter. D is equal to 4 centimeter, and DB is equal to 6 centimeter. DB is equal to 6 centimeter, which is radius of bigger circle. Hence EB is equal to DB minus D, DB minus DE, that is 6 minus 4, that is 2 centimeter. EB is equal to 2 centimeter. Since CA is 4, D is 4 and DB is 6, therefore EB is equal to 6 minus 4, that is 2 centimeter. Now we'll move towards right angle triangle AEB. Now in right angle triangle AEB, AB is equal to AE plus EB, that is equal to 4 plus 6, that is 10 centimeter. Hence by Pythagoras theorem, I'm writing this here. Our target is to find CD. I'm writing here, find CD. Hence by Pythagoras theorem, in right angle triangle AEB, by Pythagoras theorem, hypotenuse is AB square is equal to AE square plus EB square. AB square is equal to AE square plus EB square. AB is 10. 10 square is equal to AE square, we have to find, plus EB that we have found, that is EB. EB is 2 plus 2 square. 10 square is 100 is equal to AE square plus 2 square is 4. Taking 4 this side, will get AE square is equal to 100 minus 4, that is 96. Therefore AE will be equal to square root of 96, that is 16 into 16 into 6, that is equal to, taking 16 outside, that is 4 root 6 centimeter. AE is equal to 4 root 6 centimeter. Now CD is congruent to AE. And we got AE as 4 root 6 and CD is congruent to AE. Hence CD is also 4 root 6 centimeter. CD is also 4 root 6 centimeter. That is our target. CD is 4 root 6 centimeter. See once again, there are two external touching circles at point E, and radius of smaller circle of first circle is given as 4, radius of second circle is given as 6, and we have to find CD, where CD is common tangent of these two circles, which touches first circle at C and touches second circle at point D. Now there is one construction that is very important. Means from this construction we will get solution, that is draw AE perpendicular to DB. Draw AE perpendicular to DB. Now since A is perpendicular to DB, this angle is 90 degree tangent theorem, this angle is 90 degree tangent theorem. Since this is tangent radius, hence three angles are at angle, therefore fourth angle will be a right angle, that is remaining angle of quadrilateral. Hence quadrilateral CAED is a rectangle. Hence CA is congruent to D, but CA is 4, hence D is also 4. Now in DB is 6 centimeter, therefore EB will be DB minus D, that is 2. Therefore this side is 2, EB is 2. Now in right angle triangle AEB, which is right angle, since this is right angle, therefore this will be obviously right angle. By Pythagoras theorem, AB square is equal to A square plus EB square. AB is equal to A plus EB, that is 10. 10, therefore we will get 10 square is equal to A square plus 2 square. From this we will get A as square root of 96, that is 4 root 6 centimeter. But A is congruent to CD. Hence CD is also 4 root 6 centimeter. It's our target. This way we have seen touching circles, definition of touching circles. We have seen one theorem about touching circles. We have solved examples of practice at 3.2. Complete all these examples in your notebook, and also write theorem of touching circles in your notebook, and we'll stop here. and tomorrow we'll see next part of this lesson. So stop here. Thank you.